Okay, so yeah, I'm really happy to be here today presenting Quantica. Thanks, Anton and Isidora for the invitation. So yeah, Quantica is a Julia package. It's been quite some time in the making, as Anton said. The scope is rather similar to Quants, but it's for simulating tight binding systems, but it's written in the Julia language. It's free and open source. All the code is in GitHub. And actually, if you go to the GitHub page, you can click this link here down in the README, and it takes you to the documentation in case you want to delve deeper into what we will be seeing today. Okay, but I want to start by first thanking a bunch of people that were really important in this journey for me. Either discussing concepts, teaching me some physics or algorithms, discussing design issues, or even submitting code. So I'm sure I'm forgetting someone, so I apologize in advance. But I also want to thank the people on the right, which you might not know, who are part of the wider Julia community, which is, I think it's fair to say, it's a wonderful community. They're really helpful, and they've helped me very much in this journey to learn Julia and become a developer. So yeah, so I wanted to first start saying some words about Julia, the language, because I'm aware that maybe some of you are more familiar with Python and not so much with Julia. So just some brief words. Julia is a programming language that in some ways is similar to Python in the sense that it's a high-level language and it's interactive, but it's not really an interpreted language. It's an ahead-of-time compiled language, which makes it different in certain ways. However, many of the workflows that you might be used to work very well with Julia. For example, it has a REPL, which is a command line like in Python, and it works really well. You can actually do real work in the REPL. And it also has a VS Code integration. You can actually run interactive code in VS Code 2 with a plugin. And it also works with Jupyter notebooks, both within VS Code and the browser or wherever you like to run your Jupyter notebooks. So you will see later this. I'm going to use a Jupyter notebook. It has other ways to work with like Pluto notebooks, but I will not discuss those more. They're really nice though. The language has, in itself is also really interesting. It has a very rich parametric type system that is really fun to work with. And the paradigm is also a bit original in the sense that it's not an object-oriented language per se, like you might be used to. It's more like a verb-oriented language. They call it, the paradigm, they call it multiple dispatch, which makes you design your code base in a rather different way. So if you're interested, go ahead and read the manual. The Julia manual is really nice. It's a really nice paradigm. Also, it's very special in its execution methodology. It's really, as I said, ahead of time compiled, which makes it really fast. They usually say it's within a factor 2 in runtime relative to C. It can even be competitive with C. And the thing is that you don't touch a compiler ever. It all happens transparently. So you invoke a function, and this function gets, the first time it's called with a certain signature, it's compiled in the background to machine code for your platform, and then it runs that code, and then it's very fast. So it makes for a very, very interesting language for scientific computing. There's also another aspect of Julia that I really like, is that it encourages you to become a developer. It kind of blurs the boundary between the library user and the library developer. And it does so in a number of ways. First, of course, it's a free and open source language. It has a culture permissive licenses, so you can copy code around and share. And it has, as I said, a really great community. Also, it has this amazing package manager that makes it really easy to create your own packages and use packages independently of whether you're in Windows or Mac OS or Linux. It provides reproducible environments. So you set up an environment with certain packages, and then 5 years later, you will be able to reproduce your calculations, right? It also has a sophisticated compact version resolution algorithm. It can provide binaries for your platform in a way that is completely transparent to you. It will download your MKL libraries for your platform behind the scenes. So it's really, really powerful. Then there's also this aspect that blurs the line for the user, which is that you can see all the code all the way to the bottom when you're coding something, unless you use a compiled library that is, a C library. If you're using Julia code, you can really see everything that is running down to the bottom. So that is a really nice thing. So it encourages you to find bugs if you find something that doesn't work as you expected, and immediately, open an issue and try to fix it or whatever. Okay, so it's very good for our kind of job too. It's specialized in scientific computing, although it's in general. It is said that Julia is a general purpose language. Its forte is really scientific computing. It has some trivial integration with compiled libraries. You can call Fortran or C shared library just with a direct C call, because you don't have to convert like arrays, for example. The same way you store an array in Julia, the C code will just accept it because it has the same layout. It also has a very large ecosystem by this time of technical packages. Particularly interesting is the differential equations packages. Also, it's strong in linear algebra, optimization, and other specialized domains. In some aspects, I think it's not really bleeding edge. For example, machine learning is still lacking, in part because all the money is going to Python people. But it's very good for example, for high performance computing. It has all these constructs that allow you to program with concurrency, and packages that allow you to work with clusters very comfortably. So it's really nice for HPC. Of course, it has some weaknesses, and it's important to be aware of them. For the moment, Julia cannot produce small binaries for your code, although there's people working on that. The very composable nature of Julia makes that a research topic in itself. It's not easy. Also, some people that come from Python or C++, will find that there's some limitations in the language because they're used to this object-oriented programming. For example, it doesn't have multiple inheritance. It uses instead this multiple dispatch paradigm and goes about the equivalent of multiple inheritance with type composition or traits. So it takes a bit of time to switch your mindset to Julia, idiomatic Julia. Also, there's a case to be made that maybe it's too permissive. If you compare it to languages like Rust, that essentially the compiler in Rust forces some correctness guarantees on your code, Julia has very few guardrails. So it perfectly allows you to shoot yourself in the foot. Okay, so that can be seen as a weakness because it doesn't enforce a robust, ecosystem. It can be more buggy than other ecosystems, right? Although maybe that's an opinion. The errors it produces are a bit too verbose, although they're getting better with time. There's also a weakness, a sociological weakness, which is there's no big money in Julia. Really, it's not like nothing compared like Java or Python. There's no large corporate backing, and there is no quant equivalent. That is a really strong weakness until today, right? So this is my effort to remedy that last point. So Quantica is now in version 1.0, and it tries to do some of the things that Quant does. This is a list of features in Quantica. It provides a flexible but rather short, terse API to define type binding systems. It can define arbitrary dimensions for lattices and site, where the dimension of sites, I mean the number of orbitals per site. It has a strong focus on performance. So yeah, I've done my best to carefully implement everything. It uses the correct algorithms, and they're implemented the right way, so it's fast. It can provide, for example, parameter-dependent systems that get instantiated with the parameter choices that you have very fast in memory. It can compute interpolated band structures that I will show you what I mean by that. It can couple different systems, and the way it does it is through in the introduction of self-energies that are computed with Green's functions. So Green functions is the core object that Quantica uses to do a number of things, like computing observables or coupling systems. It's also extensible in the sense that it has a bunch of solvers for example, eigensolvers for diagonalizing Hamiltonians, or Green solvers for computing Green's functions, or to compute different observables. And those solvers, you can add more with time. There is a well-defined API that they have to satisfy, and you can make it grow and have specialized solvers. And you can mix and match different solvers, which is really powerful. It has a library of presets, for example, lattice presets or Hamiltonian presets. It has some visualization tools that are really rich. You can visualize most things you compute. And as I showed you, it has documentation, both in the form of doc strings with all the details of every command and a tutorial. So this is the typical workflow. When you work with Quantica, you want to get to compute some observables on the right, and you start on the left by defining first your system in terms of a lattice and a model that is defined in an abstract way independent of the lattice. You combine the two, and then you obtain a Hamiltonian. And this Hamiltonian, you can already compute things with this, like a band structure, for example, or eigenvalues. But then you can also compose different Hamiltonians by adding a self-energy to a Hamiltonian. That produces a Green function, which also has a Green solver, and that Green function can be used to compute, finally, observables that you want. So instead of discussing that on paper, now I'm going to show you a demo. Let's see how it goes. So as I said, it's the first time I do this in a talk. So I'm going to go to the VS Code Jupyter notebook that you see here. I will post it in the Mattermost later in case anybody wants to play with it. Mm-hmm. So yeah, this notebook has one section for each of these itinerary stops in the workflow. I'm going to start by loading Quantica. In Julia, you just say using the package after you install it. I'm going to use Quantica and also these two packages, glmaki and kairomaki, which are graphical backends, like say matplotlib, right? So to plot things, but this one is used to produce inline vector graphics, and this one is to produce OpenGL GPU accelerated graphics in a window. Okay, so I'm going to be using the two to show you how it works. This just defines some defaults for the plots, and I'm going to activate the kairomaki backend first. Okay, so let's see how to define a lattice. That is the first stop, no? So a lattice is defined as a bunch of sublattices and some Bravais vectors. So a sublattice is created with sublat, and you just give it a list or a collection of positions and optionally some name for that sublattice. We're going to create the boron nitride lattice. So it has two sublattices and these Bravais vectors, same as graphene, right? So if you define these two and you call lattice on them, you obtain this object. The lattice is a 2D lattice in 2D space and some details on it. And then to visualize it, you use this qplot command, which is a Quantica command that accepts a number of arguments here and some keyword arguments that can be used to customize your plot. No, so in this case, the visualization of a lattice is just the unit cell with the two Bravais vectors and the two sublattices in different colors. I mentioned we have lattice presets. So this is a common lattice, right? It's just a honeycomb lattice. So we have a lattice preset. It's a honeycomb. And well, if you just call it like this, you get exactly the same as the one above, but the names have default names. The sublattices have default names A and B. So you can change that. So they're kind of customizable to be boron and nitrogen. And then you would have exactly the same as before. Okay, so I'm going to rush through this because it's a bit long. But if anybody wants to say something, just do, okay? And I stop. Okay, so we've defined the lattice. We've visualized this lattice. We can transform the lattice, like, for example, rotate it using transform. To transform, you can pass a function. This is the syntax for an anonymous function, a lambda function in Julia. And this is a matrix. This SA thing in the front is just to make it static sized, static array, it's called. So it's just for performance. So this essentially rotates your lattice by 90 degrees clockwise. Okay, so that transforms the lattice, produces a new lattice, and this thing is the pipe operator, which essentially passes the thing on the left as the first argument to the function on the right. It's just a way to write a sequence of operations in a clean way. So in this case, I produce, yes.
Yeah, Pablo. So I'm wondering about the semantics of this. So if I understand correctly, the transformation applies both to the coordinates of the basis and the lattice vectors.
Yeah, absolutely.
But the transformation is only meaningful for the lattice vectors if it's linear.
No, because essentially what it does is it takes the point here, and so.
Oh, I see. Okay, so
this point here and takes it to where it lands.
Oh.
So it's essentially it can have the nonlinear transformations, and you just get maybe a funky distortion, but it's still a Bravais lattice.
Yeah. Okay. Got it. Thanks.
Yeah. Okay. So yeah, you see here what Anton's saying is that the Bravais vectors are also rotated as you expected. Okay. So this syntax here is sometimes called the carrying syntax. So I have a little snippet here to clarify. So this symbol, this triangle thing, essentially injects the thing on the left as the first argument to the function on the right. So you will be seeing a bit of this. Okay, so that was a transformation. Now we can do derived lattices using also supercell, which is another command that transforms lattices, and it's quite powerful. The simplest use is just to create a bigger lattice. For example, this is a 3x3 supercell of the boron nitride lattice that we had before. So you see here, if you visualize it, you have 3 times the size of the unit cell, but essentially it's the same lattice. You can also reduce the dimensionality of the lattice by defining with supercell, what are going to be the new Bravais vectors. For example, if I want a nanoribbon with one Bravais vector that is 10A1 minus 10A2, I just write it like this, okay? And that would be a Bravais vector on the horizontal axis, the x-axis. And then what to do in the other dimension. In the other dimension, I'm going to bound the system with a selector. This is a region selector that just takes an anonymous function that says that the y coordinate is going to be between -11 and 11. That creates a nanoribbon that you see just here below. So this nanoribbon, a single cell, because that's the way, is the one Bravais vector. Okay, so if you want to see more than one unit cell, you can, for example, use a lattice slice, which is just like a view into a subset of sites of a lattice. You just pass a selector, like here, a region selector, and I also added a sublattice selector for boron sites to lat. So that creates a lattice light that, if you visualize it, you see all this unit cell, this rhombi, with only one single site in each of them, because it's a boron atom. okay? That is a lattice slice. Okay, so that's the first part. We are here. Let's go to models.
Sorry, just a moment. I also have a question about the selectors. They're a bit magical in that having an anonymous function, I wouldn't know where it's 0 and where it's non-zero. How do you tell? Or
you ask all the right questions. Okay, so this implements essentially a field search. You know, when you in a field program, you click the bucket and you fill a region.
So the default starting coordinate is 0 then.
Yeah, but you can specify a different one. So it
starts
at 0 and it grows until it finds no more region.
All right, thanks.
Okay. Okay, so to define models, I mean, there's quite a bit of richness here, and I believe the quant paradigm is different. So this might be a bit unfamiliar, but bear with me. So if you want to define a type binding model in Quantica, you can do it at different levels of complexity. The simplest models are just position-independent terms. You always split on-site terms from hopping terms. So if you want all sites to have an on-site energy 3, and all sites within nearest neighbor distance to have hopping 1, you write it like this. You can put a minus or a plus, okay? So you see here that the hopping range is by default neighbors 1. This is nearest neighbor distance. And otherwise, it doesn't constrain to who this is applied. It's everybody except for this. Okay, so if you want to go to second nearest neighbor distance, you just say neighbors 2 in a range constraint. Okay, so that is a selector. That is not a region selector, it's a range selector for hopping. And then you get neighbors 2. If you want to go numerically from between distance 1 and 2, or up to distance, so that would be 1, 2. If you want to go from 0 to 2, you could just say 2 here. Okay, and these are all hoppings and on-site energies that do not depend on position apart from this constraint. But then you can have position-dependent terms. So instead of saying hopping 1, you can pass an anonymous function to on-site, for example. So this would apply an on-site energy that is equal to the x coordinate to each site in the unit cell. And for the hopping, you pass a function of 2 variables. Okay, so these 2 variables are not R1 and R2. It's actually the center of the hopping and the distance of the hopping, which makes things easier for modeling most systems. Okay. Okay, so there's also the possibility of having models that depend on position, but also depend on parameters. For example, I want a model that depends on a chemical potential that is undefined, or a hopping amplitude T that is undefined but has a default value 1. Okay, for that, we use this at on-site and at hopping functions. They are technically macros, and the reason why this at here is some technical thing. Maybe in the future, I will figure out a way of doing things without this at. But anyway, the difference now is that the function has these keyword arguments after the semicolon. So this is the positional argument, and then this is the keyword arguments. And you see that the different terms can actually share parameters. So the result is a parametric model that has a bunch of parameters that can be adjusted. So more about models. Up until this point, all the terms apply to every site. But as I said, you can constrain to which sites your on-site energy supply, for example, exactly as before with a region selector. This would be on-site energy 3 for all sites within a disk of radius 2, okay? Or this more complicated one is just hoppings between sublattice A and B at the distance 2 at maximum and within this region, okay? So you can build all these kind of complex models, and you can also combine them. You can say, for example, do this kind of combination. And this prime is just a conjugate for the hopping, okay? So hopping backwards. And okay, so final layer of complexity, you can also have multi-orbital models in which the right-hand side of your function is actually a matrix. Imagine you have several orbitals in a given site, no? So this would be, for example, a model for a spinless superconductor, because you have a matrix. Remember, this meant static array, which is a good idea to use. So it has off-diagonal pairing terms, and in the diagonal, you have your hoppings and chemical potentials. Okay, so that would be a superconductor. So you see, models are defined absolutely independent of the lattice. So if you combine a model and a lattice, you get a Hamiltonian. For example, in this case, we're going to do graphene with next nearest neighbor hopping. So that would be hopping 1, which means hopping 1 at nearest neighbor distance, and hopping 0.5 between A and A lattices and B lattices. This broadcasted arrow here means this. So A to A and B to B, but not A to B, okay? And go up to range 1, no? So that would be next nearest neighbor hopping 0.5. So I define the model, and then I just say Hamiltonian, a honeycomb lattice, and the model. And then what I get is next nearest neighbor graphene Hamiltonian. So this syntax here, you can actually rewrite it with the pipe operator like this. If you pipe lattice to a model, Quantica understands that you want a Hamiltonian, and it will just produce your Hamiltonian. Okay, so how do you visualize Hamiltonians? It's similar to lattices. I'm going to use now the OpenGL accelerated backend for this. I'm going to just activate it, and I'm going to visualize this Hamiltonian, and it opens here on a window on the right. So you see the Hamiltonian is, again, the unit cell, but it also has, in transparent mode, all the sides that are linked to the unit cell by hoppings. So you have nearest neighbor and next nearest neighbor. So this inspector true thing that I used here allows you to debug your Hamiltonian by having tooltips with the on-site energy and the hoppings. For example, the nearest neighbor hopping is 1, correct? And the next nearest neighbor hopping is 0.5. Okay, so that's and you can zoom in and zoom out with this backend. So that works. Okay. What about more complicated Hamiltonians? I'm going to use this model that you see is multi-orbital. It has parameters. One of the parameters is an electric field, is actually a vector. Well, other than that, it's not so complicated. I just use...
Pablo, there is a question. Johanna, please.
Yeah, sorry, yeah.
I just had a question, but maybe you're going to answer it. So how does this inspector work if you have like position-dependent hoppings and so on? I mean...
Very good, very good. So, okay, this is a very important point. So when you do a model, this model is applied to the unit cell, okay? And every unit cell will be a copy of that. So all unit cells in a Hamiltonian are by definition identical. Okay, so if your Hamiltonian has a position-dependent term, for example, a magnetic flux that depends on position, and you want your Hamiltonian to really have these position-dependent hoppings, you need to first enlarge your unit cell with supercell and then apply it to that.
Okay.
Okay?
I get it. Yeah, clear.
Okay, okay. So I'm afraid I don't see the hands being raised. So Anton, if anybody has questions, just stop me, okay?
Yeah, will do.
Okay. So multi-orbital Hamiltonian. Okay, so I have this model here. I'm going to do a cubic lattice, so 3D lattice now. It's another preset. LP is lattice preset, okay? Supercell 4x4x4. And the Hamiltonian is going to have this model here, and I need to specify that it's got 2 orbitals because Quantica is not smart enough to look inside the functions and figure out it's a 2 orbital. If you don't do this, it will complain, but only after the fact. So if you define this, you see it's a parametric Hamiltonian because it has a bunch of parameters. I can instantiate, for example, one parameter E, okay, by this call syntax. So h of E equal a different vector will just produce a Hamiltonian instead of parametric Hamiltonian without free parameters. Now this is totally specified. And I can, of course, visualize this again. So in this case, it's 3D, and I can, navigate this. And actually, I use the inspector, so I can actually also see the matrices on each side. You see that the on-site energy is the same 5. It's not the same 5, 4, 3, and 2. This is what Michael was asking. So within this unit cell, it has an electric field, but when you go to the next unit cell, boom, it's 2 again, because it's by definition periodic. Okay. Okay. If you wanted to have a finite size system, you use supercell without Bravais vectors, and then you would get a big finite size system. Okay, so what about performance for big models? I'm going to do a bigger lattice for about 600,000 sites and 4 million hoppings. It's going to be a 0-dimensional lattice in the sense that it's not periodic, defined within a certain region that I just cooked up here. The model is going to be just a simple parametric model with an electric field. It's going to be a cubic lattice. And supercell, you see there is no Bravais vector, so it's just bounded, a bounded region. And I'm going to just use the model up top. So I run this. I get a parametric Hamiltonian. And if I want to instantiate parameters, again, I use the call syntax. And you see that the instantiation is really fast. Even for 4 million, all these sites, it's really fast. If I want to visualize it, even at these big sizes, the GPU backend is pretty good. So it actually allows me to visualize the thing and debug it. And even later, I could plot on top of this. You will see this. Plot on top of this kind of lattices some observable quantities that you might be interested in. So there's no problem with big systems. Okay, so I showed that you can instantiate parameters like this with the call syntax, but how do you get to the actual matrix of a Hamiltonian? No, how do you get the Hamiltonian matrix? So this is not what I wanted. Oh, sorry. Yeah. Okay. Yeah. This I'm gonna use this Hamiltonian now, the one we did before. Okay. So if I want the matrix of this 3-dimensional system at Bloch momenta 0, so Bloch phases 0, 0, pi, I again use the call syntax, but the first argument is going to be the Bloch phases. And optionally, I can also pass parameters. So if you do that, you get the sparse array, which is an actual Bloch Hamiltonian. Okay. This sparse array you can convert to a dense matrix, as you do in Julia, generally, is using the matrix constructor. And you will see here that the parameters are correctly implemented. Okay, so this I'm going to skip. It's not so interesting. Let's go to band structures. Right, so imagine you have the simplest model, graphene. You use the preset because it's so common. So I just set A0, the lattice constant, to 1. You can see here, the lattice is very simple, nearest neighbor. And I can compute the spectrum of this Hamiltonian, for example, at the gamma point by using spectrum, and here the Bloch phases. And you get eigenvalues, eigenvectors, just as you expect. You can also compute the band structure. It's a 2D system, so the band structure is a 2-dimensional. You use for that the command bands. First argument is the Hamiltonian. Second argument is a collection of flock faces along the direction 1 and a collection along direction 2. If you compute that, you can visualize it and you get the band structure. Okay. You see, what is interesting here is that there's a couple of things. So first, well, inspector allows you to see the degeneracy and energy of each point. You see that the Dirac points were identified as having degeneracy 2. This is actually more tricky than it seems, because what you're seeing here is not just eigenvalues, it's interpolated eigenvalues. So it constructed a continuous mesh that connects eigenvalues properly, and it does so by comparing the overlap of eigenstates and dealing with degeneracies in a smart way. So this way of computing band structures is actually useful for other things later. You can also take a band structure of a 3D system, which is a 4D manifold, okay, which you wouldn't be able to plot, and actually plot it by slicing it at constant energy, for example. So I'm going to do a cubic lattice, and I'm going to use a simple 2-orbital Hamiltonian, okay, with a Zeeman field in the on-site term. Think of it as a spin. And the bands, if I don't specify the block faces, it takes some default. It has a lot of edges and simplices, but if I just slice it with this syntax, I say momenta are undefined, but energy is minus 0.9. It reduces it to a 3D manifold that you can visualize. This is the Fermi, actually the Fermi surface of the square lattice with a Zeeman field. Okay, that's another thing you can do. More work with band structures. You can do a line cut of a band structure, which is something you very often need. I'm going to go back to inline plots here with Kairomaki. Say you want a line cut of graphene from gamma to K to M to gamma. Okay, so what you do is you define a set of values for these nodes in the x-axis, 0, 2, 3, 4 here, and subdivide these intervals with 10 points with subdiv. And that is going to be your second argument, the mesh over which the band structure will be computed. And then you map each of these points to the nodes that you want your path to go through, gamma, K, M, gamma. So it has, Quantica knows a bunch of names for special high symmetry points in the Brillouin zone. So if you do that, you get a 1D band structure that you can plot, and it does what you want. So if imagine here I put 1, 2, 3 instead, what it does is it just makes them equally spaced, okay? Right, so I mentioned at the beginning that we have like extensible solvers. For example, eigensolvers, we have a bunch of them. Everything I showed you uses the standard linear algebra eigensolvers in Julia, which computes eigenvalues for dense matrices, so every eigenvalue. But of course, our matrices are very often sparse and very large, so you would want to use kind of Arnoldi methods or Langsus to compute a sector of the spectrum. So you can do that. I'm going to show you, for example, in this Hamiltonian here, it's a square lattice for 4 by 4. Let me plot it. So this is just a nanoribbon, okay, with a period 4. So I'm going to use bands again. Since it's a 1D lattice, I'm going to use just one mesh, 20 points. And as a solver, I'm going to combine an eigensolver. ES is eigensolvers, okay? So we have a bunch of these. So I'm going to combine Arnoldi method, which is a Julia library, asking for 14 eigenvalues. But I'm going to wrap it up in a solver called shift invert around energy 0. So it's an internal eigenvalue problem now. So you do that, and you plot it. You see you have this bunch of 14 eigenvalues for each of the phi phases. So the subdiv here. Now, nice thing about this plot is that the interpolation between eigenvalues that I mentioned makes it possible to actually distinguish the bands among this jumble of eigenvalues, which with more standard approaches in which you just compute eigenvalues, you would see nothing. This is what you would see with this kind of mesh. So interpolation of bands is really powerful in this sense, no? It allows you to use meshes that are rather coarse. More things that you can do with bands. You can use special shadings to encode information about eigenstates. I'm going to define here a Kahneman-Melle model. So it's graphene with a spin orbit for spin up. So it's a 2x2. Sorry, no, it's a scalar. It's not 2x2. It's just a scalar. It's for spin up, say. And I'm going to compute the bands along a line cut, but I'm going to use a shader now for qplot. So qplot here, this command, this keyword argument here, opacity, is going to take a function of eigenstate, energy, and block phase. Okay, and I'm going to use this function to obtain a number for each point along a band. So that is going to be an opacity shader that is going to give this result. So it encodes information, and you can do that also through the color channel, for example. I'm going to show you another example in 2D. So this is the same Hamiltonian, the Kahneman-Melle, okay? But I'm going to compute now the bands in 2 dimensions, okay? Forget about this mapping. This is a more advanced use of mapping. And I'm going to plot it using the color shader. So color is going to encode information about the eigenstate now. So you see here on the right that each point on the surface is actually the angle of the spinner, of the pseudospin, in the plane. Okay. So you can actually combine different channels like opacity and color to obtain, really complicated stuff. No, it's very tunable. Of course, qplot has a very large number of keywords that you can check. It's all in the documentation. Okay, so we're almost finished now. We go now to green functions. So green functions is going to take us to coupled systems in a bit. But first, I'm going to show you how to compute the Green's function of a simple system, for example, a nanoribbon. And that's just one step up from the Hamiltonian complexity. You know? So here I have a lattice. I do a supercell of the lattice. I apply a model. And this Hamiltonian here, I'm going to pipe it to Green's function. And this is one of the solvers in Green's function. This is the Schur solver, which is essentially what I think what Quant uses for leads. It's the kind of algorithm from Michael's thesis, no? So if you do this, you get this object, Green's function. You can also plot it. In this case, it's a very simple nanoribbon like this. And then this G, you can evaluate it to obtain the actual Green's function, but you can do it in 2 steps. You can, for example, specify only the energy and any parameters in the model. So this partial evaluation at fixed energy. And that would do some work depending on the solver that is able to be done when you know the energy, okay? So you evaluate that. Or you could actually fix not energy, but positions. Instead, imagine you want some sites on this lattice specified by this region. For example, that would be those sites here. I plotted them with the qplot bang command. So this syntax here, G with square brackets, is fixing the positions for the Green's function, not the energy. So this is energy, and this is a position. Or you could actually fix both, do a complete evaluation, fix the position parameters and, energy parameters and positions. And then you get your actual Green's function, which is a 9x9 matrix because there is 9 sites in this selection. Okay, this is a bit complicated, I know, but it's all rather slowly explained in the tutorial if you want to read it. So once you have a Green's function, you can compute observables, no? For example, I'm going to show you the local density of states in a closed lattice, zero-dimensional cavity, and I'm going to add some magnetic flux to make it more fun. So I define a region, and it's kind of a star-shaped region, and I'm going to fill that region with a square lattice using the supercell command again. And in my model, I'm going to introduce this Peierls phase. Cis is essentially the complex exponential. It's cosine plus I sine. Okay, that's a Julia thing. So that is a Peierls phase. So it's going to implement a magnetic flux, and I'm going to build a Green's function with that. If I don't specify the solver, it uses the default solver for this kind of Hamiltonian, which is in this case a direct inversion solver, LU factorization solver. So this is the visualization of the Green's function. At the moment, it's just the region, like the Hamiltonian. And I'm going to now compute the local density of states at certain energy. I'm going to fix the energy to 0.11, for example, and I'm going to say zero magnetic field. So this thing is going to be a partially evaluated Green's function, a green solution that I pass to LDOS. So LDOS constructs this object that is local spectral density solution that can again be evaluated at different positions now to obtain the actual local density of states. I could do that, or I could actually plot it. I'm going to use this rho as a shader for this lattice. I'm going to encode the local density of states both in the color of sites and the radius of sites. So if I do this, I get the lattice, but now the sites encode the local density of states. And I could change the, I don't know, the energy. And you get a different local density of states. This exactly the same way as the LDOS, you can compute the current density at a given energy. So if there is no magnetic field, there will be no currents, right? But if there is magnetic field, you will have current circulating in the system. So I'm going to fix the energy to 0.1 and a finite B field and pass this to the current command. And that builds...
there is a question, Pablo.
So,
yeah, I had a question, Pablo. So basically, so do I understand correctly, this is a finite system, right?
yes.
So you will have discrete energy states, right? So there's some kind of broadening.
There's some kind of broadening, yeah. I didn't want to go into those details. You can actually pass an imaginary part to the energy. Okay, everything works with complex numbers, like this. But if you don't, so you just get some broadening there. If you don't, it actually does a default broadening by the square root of epsilon, so machine precision. So you always have a minimum width to every single level.
I see. Okay. Yeah.
Okay. And since there are many levels here, you were able to actually see the profile in space.
Yeah, but I could just as well take the Hamiltonian and calculate the eigenenergies also from there, right? The wave functions directly.
Absolutely. That would be exactly. That would be another way to just plot the eigenvalues, eigenstates. You could compute them with spectrum like before. The spectrum command would give you both energies and eigenstates. Yeah. And you could also use those as a shader for side color and side radius. Anyway, it's kind of, I have no time to go into all the possibilities, but there are many possibilities here. Yeah. So current computes the current along different hoppings in the system. Okay. So if I build this J and use now J as a shader for the hopping radius and the hopping color, what I get is a plot of the lattice. I'm going to hide the sites are going to be tiny. So this just these little points. But now the hoppings have a color and a thickness that is a function of the current. You see here all the edge states due to the magnetic field. Right. So that's a finite cavity. You can also, for example, take a semi-infinite lead. Okay. So I'm going to build now a lead with some off-diagonal on-site terms, some whatever model that doesn't matter much. And I'm going to define a square lattice with this Hamiltonian and a supercell that is a nanoribbon, as before, like one single Bravais vector along the x direction and bounded in the y direction from 0 to w. W is going to be an argument to this lead. It is just to show different possibilities. So this G lead is going to be a Green's function of the lead itself. And again, I'm going to use the Green solver, the Schur Green solver, but I'm going to add a boundary at 0. 0 means cell with index 0, the unit cell at the origin. So if I build this thing, I'm going to use now the inline graphics again. I can, exactly the same as before, do LDOS at a fixed frequency, fixed energy, but again, the position is not fixed. So as soon as I pass this raw as a shader to qplot, and I say, hey, give me a plot of 100 unit cells from 1 to 100, it will compute the density of states for each of them and use that as a shader, and you get the plot here. So a unit cell is just one row of atoms. This is just 100 unit cell, and you see that it computed the Green's function at different positions. Sorry, the local density of states. Okay, so that is visualization. You could, of course, just numerically compute the local density of states, for example, as in the first unit cell. Here I'm fixing position instead of frequency, and now I'm going to evaluate the sum of the local density of states at different energies from minus 0.15 to 0.15. Well, it turns out this model that I wrote is actually kind of like a superconductor, so it has a gap and some coherence peaks, and then you can just obtain this familiar local density of states plots. So bear in mind that this is not a finite size system. It's a semi-infinite system. So it's the solver, as you know, is non-trivial here. So finally, I get to attaching different systems together. So I want to do this kind of typical multi-terminal cavity thing. So for this, I can define first a central region, which is what you see here. It's going to be a circle. RP is region presets. There's also some geometric presets in Quantica. So it's a circle combined with a rectangle horizontally and a rectangle perpendicular vertically. So it's this kind of shape. Okay. And then some leads that are not shown here. That is just, the y coordinate from minus 25 to 25. So this is two regions, and now I'm going to build the Hamiltonian for the central region as before, as we've done a lot of times now. And the lead, as we've done again, is going to be just a nanoribbon in the right direction, okay? So that gives you just the Green's function of one lead going from 0 to the right. And I'm going to define this function that just rotates coordinates by 90 degrees. And I'm going to use the attach command. So attach just combines systems by attaching a self-energy to a Hamiltonian. There's many uses to attach, but this is just a simpler one. You get first argument, which is the Green's function that you use to compute the self-energy, and a region that is the sites in H0 to where the self-energy will be added. So I'm going to attach the lead on the right with this line, then the lead on the left with this one. The reverse true reverses the lead. Then I'm going to rotate the lead 90 degrees to do the one on top, and I'm going to rotate and reverse to do the one on the bottom. So this creates 4 contacts. The concept is now a contact which is a subset of sites with a self-energy. And when I pass that to a Green function, this Green function keeps track of all these self-energies. So when it evaluates, it uses that information. So for example, here, I'm going to use this syntax that we saw before, but for position, I'm going to specify that I'm going from 1. This integer means contact 1, which is this surface, to any site in the lattice, okay? Which is basically the propagator from any site here to any site in the system. I'm going to take the absolute value to be able to plot that in space. And I'm going to use this matrix as a site shader and a site radius shader. And as you see, I get this nice kind of Green's function representation. No? You can see it's a rather big system, but of course these solvers are really optimized, so they work very, very fast. With these Green's functions, I can not only compute this kind of things, but transmissions and conductance and other things, as you can imagine. This would be, for example, an example of transmission from lead 1 to 4, from here to here. Non-local conductance from 1 to 4, so changing a bias in 4, looking at the current in 1, and local conductance 1, 1. So that, if I evaluate those for fixed energy, I get these numbers. And okay, so this was just the typical kind of thing the quant does, right? So using some leads, I have to confess, I don't use quant, so I'm not so familiar with it, but I believe this is the idea, that it uses some solvers for the leads and then does the transmission. If we want to do more complicated combination of systems here, I could, for example, consider not just leads, but 2D systems, infinite instead of a lead. No, I'm going to do, but that requires a different kind of solver. I'm going to do a plane that is a square lattice that has a certain band structure, very simple band structure, which is this. And I'm going to use this band structure to actually solve the Green function for this infinite plane. This is a solver which is not very optimized yet because it's very new. It's a bit of experimental. So if I pass that as a solver, Green solver bands actually uses the band structure to compute the Green function. So I'm going to also attach a contact that is defined not through a lead, but just a model, Hamiltonian, just an imaginary part in one site at a certain position. And I'm going to plot the Green's function. So this takes a bit of time because there is a boundary, and this boundary makes things more expensive, and takes about 25 seconds. But this is the result. So you see, this is an semi-infinite plane. The boundary is here at 0. This is the point where I attach the lead, and this is a Green's function throughout all the plane. I could evaluate it at any point. And the way this is done is by taking each and every of these simplices and summing up their contribution to a Green's function, which has an analytical expression. So it's another very interesting solver for higher dimensional systems. So I'm going to stop here. It's already 1 hour long. So any questions that you want to make is your moment now.
This is really fascinating. Out of curiosity, what solvers do you have implemented for the Green's function for the lead self energies?
Can you repeat? Sorry.
What solvers do you have implemented for the Green's function and the lead self energies? Yeah,
you mentioned in Slack the Sancho solver. This is kind of I'm going to show you for Green's function. We have these solvers. Okay, so you have KPM, which is really nice, and you have this Sure. This Sure is kind of the Sancho solver on steroids. This is really a one-shot version of the Sancho solver. So it doesn't need to iterate. It's just one linear algebra operation. You can read Michael Wimmer's thesis for details on this.
Sure.
And you have a KPM, so kernel polynomial method solvers. You have direct solvers. Each of them is good for a certain system. For example, sparse LU factorization solvers only works for cavities that are bounded. So L equals 0 means 0-dimensional lattices. Same for KPM. Sure is good for one-dimensional cavities, and bands is for higher dimensional Hamiltonians.
Mhm. Right. Thank you.